Hello and welcome to lecture number 13 of Optical Instrumentation. In our previous lecture, we started Michelson interferometer. We discussed few applications of Michelson interferometer. In this lecture, we will continue and complete the applications of Michelson interferometer. Then, after that, we shall discuss Fabry-Perot interferometer and Rayleigh's refractometer. So, topics for this lecture is refractive index and thickness of thin transparent plate. So, we have seen how to calculate the how to find out the unknown wavelength of monochromatic light. Also, we saw how to resolve two spectral lines of monochromatic light. Now, next application we shall see how to find out the thickness of thin transparent plate, and if we know the thickness, how to find the unknown refractive index of the transparent glass plate. Then we shall discuss another interferometer, that is Fabry-Perot interferometer. We shall discuss its construction, working, and how it is different from Michelson interferometer. Then one refractometer also we have to study, that is Rayleigh's refractometer. So, determination of refractive index of and thickness of thin transparent plate. So, what happens, as you know the construction of Michelson interferometer, let me draw it here. So, this is a simplified construction of Michelson interferometer. This is monochromatic light source S. So, monochromatic light is traveling in this direction towards right. This is a semi transparent glass plate, 50% with 50% transmitting and reflecting properties. So, we keep this plate at 45-degree angle with the incoming light. So, half of the light will be transmitted and half will be half of the light will be reflected and half will be transmitted. So, these are two mirrors, one is AM1, another is AM2, one mirror is movable, another mirror is fixed. So, what we get an interference pattern on this screen, and when we move the movable mirror, the fringes of this pattern are shifted. We count the number of fringe shift and we calculate the shifting of mirror through vernier caliper, and we can calculate the wavelength of unknown wavelength of monochromatic light. Now, in this arrangement, if we insert a glass plate, either in this arm or in this arm. So, what happens? We have inserted a glass plate of thickness T and refractive index mu. Thickness is T, this is refractive index. Okay. So, thickness is T and mu is refractive index. So, what happens when we insert this glass plate, the path difference of this light ray and this light ray will change, and due to this change in path difference, the number of fringe that are shifted will also change. Okay. So, how much path difference will be introduced due to this glass plate? So, earlier the light was travelling through air. What is the refractive index of air? 1. Now, for this thickness, when we place a glass plate, now light has to travel through this glass plate. So, earlier the air was travelling through refractive index 1. Now, earlier the light ray was travelling through refractive index 1. Now, the light ray is travelling through refractive index mu for this distance t. Okay. So, in this way we can calculate the path difference. So, what is the path difference? Refractive index of glass plate minus 1 into t. So, this is the path difference that is introduced when we keep this glass plate in the path of this light ray. Now, light ray has to travel through this glass plate twice, one while it is going in this direction and another while it is coming back in this direction. So, 2 times light ray has to travel through this glass plate. So, what is the total path difference? 2 mu minus 1 into t, and due to this there will be a number of fringe shifts. So, how many number of fringe shifts we are going to calculate, and what is this? This is equal to n lambda. This we have seen from in earlier lecture, 2d is equal to n lambda. Overall path difference that is introduced is equal to number of fringe shifts into wavelength of monochromatic light. So, this is number of fringe shift and this is wavelength of monochromatic light. N lambda is the overall path difference and it is equal to 2 mu minus 1 into t, okay, where t is the thickness of transparent plate and mu is refractive index of transparent plate. So, using this formula we can calculate the unknown refractive index of thin transparent plate if thickness is known, and if thickness is unknown and refractive index is known, then we can find out the thickness. So, one quantity we must know, either mu or t, another we can find out very easily using this formula. So, let us see a problem. Okay. So, a thin transparent plate of refractive index 1.5 displaces 10 fringes when it is introduced in one of the arm of Michelson interferometer. What we have to calculate? We have to calculate the thickness of the plate and how much wavelength is given of a wavelength of monochromatic light, 6000 angstroms. Okay. So, what is given? Mu is 1.5, number of fringe shift n is 10, wavelength lambda is equal to 6000 angstrom, okay, and we have to find out the thickness T. We know the formula. What is the formula? Okay. Let us substitute the values. We have to find out T. So, by rearranging, T is equal to n lambda divided by 2 mu minus 1. Now, what is n? N is 10. What is lambda? 6000 angstrom, that is 10 to the power minus 10 meters, and 2 1.5 minus 1. Okay. So, this will be 0.5 and 2 into 0.5 is 1. So, what is this? Thickness is 1, 2, 3, 4, 6 into 10 to the power minus 6 meters. This is the thickness of thin transparent plate. We can also write it in another units, that is 6 micrometer. Okay. So, in this way we can find out the unknown thickness of transparent plates. Fine. So, as you can see, the thickness of this plate is very less in micrometers. So, the resolution of Michelson interferometer is very high, and we can find out the thickness of very thin transparent plates, very thin. Okay. Let us move forward. Okay. So, this is the solution. Fine. T is equal to, this is in centimeters, you can convert it either in meters or in micrometers. Now, next, now we will have to find out the value of mu in an experiment for determining the refractive index of air. So, we have to determine the refractive index of air with a Michelson interferometer. Using Michelson interferometer, a shift of 150 fringes is observed when all the air was removed from the tube. Okay. So, what we are doing, we are inserting a tube in one of the arm, in both the arms, and for one arm we are removing the air, and now there is vacuum. Okay. So, we shall see how many fringes are shifted. We can find out the part difference, and if we find out the part difference, due to this we can easily find out the refractive index of air. Okay. If the wavelength of light used is, how much wavelength? 4000 angstrom, and what is the thickness or length? It is 20 centimeters thickness or length of the tube. So, let us solve this. N is 150 and lambda is 4000 angstrom, that is 4000 into 10 to the power minus 10 meters, and T is 20 centimeter, that is 20 into 10 to the power minus 2 meters. Okay. So, what is the formula? N lambda is equal to 2 mu minus 1 into T. So, we have to find out mu. So, mu is equal to, by rearranging, n lambda divided by 2 T plus 1. Okay. So, let us solve this. N is 150, lambda is equal to 4000 into 10 to the power minus 10 to, what is T, 20 into 10 to the power minus 2 plus 1. So, 2, 2, and this is 10 to the power 2, this is 10 to the power minus 2. Okay. So, let us solve this. One, two, three, 4, 5, 10 to the power minus 5, 15 into 10 to the power minus 5 plus 1. So, how much is the refractive index? 1.00015. Okay. So, this is the refractive index of air, almost equal to 1. Fine. So, this is how we can find out the refractive index of either thin transparent plate or of any material. If we use a tube, we fill that tube with that material, and in this example we have calculated the refractive index of air. Okay. So, moving ahead. So, this is the solution over here. Fine. So, moving forward, let us discuss Fabry-Perot interferometer. This is the construction of Fabry-Perot interferometer. In Fabry-Perot interferometer, there are two semi-reflecting glass plates separated very small with a very small distance. So, what happens when a monochromatic light ray comes? It goes multiple reflections like this, and then multiple reflected rays are focused on a single point on the screen using a lens. So, due to this, the pattern that we get in Fabry-Perot interferometer is sharp, it is more widely spaced. Okay. So, Fabry-Perot interferometer makes use of multiple beam interference. So, in Michelson interferometer there were only two beams, but in this multiple beams are interfering with each other. So, it consists two parallel surfaces with semi transparent highly reflecting coating. Due to this, what we get? We get a circular fringe pattern that is similar to Michelson pattern, but fringes are thinner, more brighter and more widely spaced in comparison to Michelson interferometer. Okay. So, it gives a better pattern if we compare it with Michelson interferometer. So, this is the construction. Another diagram. The phase relationship between the transmitted rays depend at the angle at which each ray enters the cavity. So, which cavity? This cavity over here, this part between two parallel transparent plates. So, as you can see, the ray is entering at an angle alpha. Okay. So, it depends on the alpha, the phase relation depends on this angle, it is reflecting multiple times, and then we are using a lens, partially silvered glass plates. Multiple reflected rays are out of phase by a constant increment, increasing the sharpness of the interference maxima. Okay. So, this is the screen, form concentric circles. So, what is the condition for maximum? 2D cos alpha is equal to m lambda. In Michelson interferometer, we remember it was 2D is equal to n lambda. Okay. So, this is number of fringe shifts, 2D cos alpha is equal to m lambda. So, where is alpha? This is the angle alpha. Okay. So, they are also more resist to environmental conditions. Why? Because in Michelson interferometer both rays travel different paths. So, if one ray experiences different environmental conditions in comparison to another ray, so there will be error. But in Fabry-Perot interferometer, all the rays they experience same environmental conditions. Okay. So, due to this, the pattern is more correct. This is why we say that Fabry-Perot interferometer is more resistant to environmental disturbances than Michelson interferometer. Environmental disturbances than Michelson interferometer, because the optical path is common, because they travel a common optical path, they do not go at different optical paths. Okay. Also, if there are temperature changes in the measurement field, the phenomena will be more evident. Okay. So, after Michelson interferometer, we shall discuss Rayleigh refractometer. It is a very old instrument, but it still is used. Still today, it is used for calculating the refractive index of unknown materials, for finding out the thickness. Okay. So, still widely used for determining the refractive index of fluids, gases and liquids. It is not generally used for solids, but it is used for finding the refractive index of fluids, liquids and gases. So, it is also a split beam instrument like Michelson interferometer. So, one beam is divided into two rays. One ray works as reference beam. Another ray works as test beam, because it will travel through the test material, okay, like in Michelson interferometer. The refractive index of the unknown can be determined by the displacement of its fringes from those of the known material. Okay. So, first we find out for a known material the refractive index for that material for which we know the refractive index, and then we go for unknown material. So, this is a construction of Rayleigh's refractometer. So, you can see this is source of monochromatic light divided using two slits. We divide it into two light rays. Okay. Out of these two light rays, one they go for two paths. This is T1 tube T1, this is T2. So, normally one is filled with reference material, with the material for which we know the refractive index, and another is filled with test material, or one is kept empty and another is filled with test material. Okay. And these are discs C1 C2 that are used for adjusting, and then there is a lens, and over here we get interference pattern. We can record that interference pattern. So, by using the same concept that we used in Michelson interferometer, we can find out the formula very easily. How? So, total path difference that is introduced due to this refractive index of unknown material. So, let us consider that there is air in this tube. So, this is a reference beam. So, the refractive index is 1, and let us consider over here a material is filled. First there was air, then we fill it with the material of unknown refractive index. So, the beam will travel different path from this beam. Okay. So, there will be path difference. How much path difference? Refractive index mu minus refractive index of air into thickness of this tube. So, this much path difference will be introduced, and this is equal to n lambda, where n is number of fringe shift and lambda is wavelength of light. So, we will count the number of fringe shifts. So, what is the formula for Rayleigh's refractometer? N lambda is equal to 2 minus 1 mu minus 1 into T. Do not confuse this formula with the formula of Michelson interferometer. For Michelson interferometer, there is a 2 over here. Okay. So, a problem for finding the unknown refractive index. When one of the tube of Rayleigh's refractometer is fully evacuated, the other tube remains filled with air at atmospheric pressure. 150 fringes cross the field of view. The wavelength of light that is used is 5000 angstrom. The length of tube is 25 centimeters. Now, we have to calculate the refractive index of again air. So, what is n? N is 150. What is lambda? Lambda is 5000 angstrom. Let us convert it in centimeters, minus 8 centimeters, and we have T 25 centimeters, and we have to find out mu. We know the formula for Rayleigh's refractometer. Okay. So, what is mu? Is equal to 150 into 5 into 10 to the power minus 5 divided by 25. Okay. So, this is 630. So, mu is equal to 1.00030. So, this is the refractive index of air that is calculated using Rayleigh's refractometer. Okay. So, this is the solution. So, this was all about Michelson interferometer, Rayleigh's refractometer and Fabry-Perot interferometer. Thank you.